Okay, so on Friday we were talking about the laws of thermodynamics, okay? And we had left off where we had talked about the first law of thermodynamics, which is just the law of conservation of energy. Energy can't be created or destroyed, okay? You can increase energy to a system by doing work or adding heat, okay? And by the same token, a system can do work or transfer heat, okay, to something else and lose energy. Okay, but the energy is still conserved, it's just going somewhere else, right? And then we just had started looking at the second law of thermodynamics, which is that heat flows from hot to cold, okay? The idea that heat energy flows from hot to cold, okay, along with the first law of thermodynamics, is why a perpetual motion machine cannot exist, okay? First off, it's always going to be losing energy to its surroundings and would eventually stop unless it could create energy, which would then violate the first rule of thermodynamics. So it's one of those situations where, you know, rule number one, do this. Rule number two, see rule number one. Okay, it's kind of one of those situations. Okay, all right. So the idea of the second law of thermodynamics is that energy flows, and it flows in a certain direction. If we can put something in that flow, it's the same as kind of putting a dam in the middle of a river. Okay? We're using the flow in order to do work. Okay? Because we know the energy has to go from A to B. If we put something between A and B, it can be used to do work. All right? That's the idea of a heat engine. Okay? The heat engine has been it's now a practical construct, but a theoretical construct for a very long time. Okay? And that is, as long as you know heat is going from one place to another, okay, matter generally goes with it, okay, and as a result, you can use the moving heat and matter to do useful work. All right, so that's what this diagram here is showing. Okay, this is the heat engine. Okay. And in a heat engine, okay, when heat flows from high temperature to low temperature, this heat can be converted into mechanical energy, right? So as long as I put the heat engine here between the high temperature and the low temperature, okay, I'm going to steal some of that thermal energy and convert it into mechanical energy. That's going to do work, okay? Am I going to get all of it? Never, no. A lot of it is still going to end up going to the low temperature area and not do anything useful, okay? But I can get some of it. Right? And I can use that to do work. Right? So, in an internal combustion engine, the fuel in the combustion chamber burns. Okay? And it burns at a very high temperature, and that causes the gases in the piston to expand. Okay? And when they expand, they push down on the piston. That's what creates the power and driving force for an internal combustion engine. Okay? So that causes the piston to move. They gain mechanical energy. The remaining energy, there's a lot of it. Okay, burning gas is hot, really hot. Okay, most of that, okay, is expelled as heat through the exhaust. I mean, if you've never noticed that, the gas coming out the tailpipe is hot. Okay, but that's not where all the heat goes. Okay, I mean, your engine is metal, and it gets really, really hot, several hundred degrees most of the time. Okay, we use water plus coolant in order to keep the engine block from getting overheated. Okay? If your engine block begins to overheat, what do all solids do when they get hot? They expand. Okay? Now, if that engine block expands enough, what can happen is it can squeeze the pistons. Okay? Because the cylinder that the piston is moving up and down in, okay, is also metal. Right? As the metal around it, in what we call the block, the engine block, okay, begins to get hotter and hotter, it expands. That doesn't make the cylinder get bigger. It makes the cylinder get smaller, okay, because the metal around the cylinder is expanding, and it pushes into the cylinder, which makes it harder for the piston to go up and down, because it's effectively being squeezed. Okay? So if the engine gets too hot, okay, then it actually becomes kind of a feedback loop. Okay? The engine gets really, really hot, it expands, it pushes on the pistons. Okay? The pistons have a harder time moving up and down, there's more friction, the engine gets hotter, okay? And eventually your engine could seize. Okay? Or you could throw a rod. Okay? That would mean that the rod that's connected to the bottom of the piston that goes to the drive shaft just simply snaps. okay, because there's all this torque and no movement, and things just break. Okay, those connecting rods can go through the sides of cylinder walls, and at which point your engine is toast. Okay, so if the little temperature light comes on in your motor, you should pull over. It's one of those important warning lights you should listen to. Okay, same with the low oil pressure light. That's another one that's really important. Either one of those lights goes on, it's time to pull over. Check engine, that's usually a sensor. Your car's not going to run great, but it's probably not going to explode. Probably. I'm not going to guarantee that, but okay. If either one of those major lights comes on, I mean, there's a reason the check engine light is yellow, and the temperature light and oil pressure light are red. Okay, you got a red light, it's time to pull over. Okay, and that's simply because of the second law of thermodynamics. You got a lot of heat coming from that detonated fuel, that burned fuel, makes the whole engine get hot. Okay, all right. All right, so hypothetical temperature difference boat. Okay, so this was a design, one of the original designs for the heat engine. It's highly impractical. It's only a theoretical design, just to show that here's something that could work, maybe. So what they have is this boat that's got two chambers. Okay, one chamber has a short pipe that is in the water near the surface. So all the water that's in this chamber is warm because it's the water that's at the surface. This other chamber on the other side has this really, really long pipe that goes deep down where the water is cold. That's dumb, but it's only theoretical. Okay? So the idea here is that because these two chambers are connected, energy is going to want to flow from the warm water to the cold water. If you put a turbine in the middle, it'll turn the turbine, which will propel the boat for free. Which, oddly enough, can work. The problem is dragging that deep pipe. Okay, that pipe that goes really deep is going to catch bottom, okay, and drag, and that's really not going to let you go anywhere. Okay, but theoretically, this idea can work, and in fact, this is the basis for the jet engine. Okay, a jet engine is a series of turbines. Okay, and on one side of the turbines is the combustion chamber, where the kerosene jet fuel is burned. Okay, and it burns really, really hot. And then there's the other part that's behind the turbines where the really cold, high altitude air is. Okay, the bigger you can make that temperature differential, the more thrust you get. Okay, so if you want to get more thrust, you simply add more heat. Yeah, well, more heat, more fuel. Okay, throttle up, more fuel goes in, burns hotter, pushes more. Okay, throttle back, not as much fuel, engines don't spin as fast, you don't get as much thrust. That's how a jet engine can work. All right, so heat engine, jet engine. Now, heat pumps are the other thing. Now, we briefly talked about how your refrigerator works. Okay, your refrigerator and your air conditioner are heat pumps. Right? What they do is they're active transport for energy, okay, or for heat, or for thermal energy specifically. Okay? So you put the meal you just finished, it's still a little bit warm, but you want it for leftovers tomorrow. You take it and you put it in the fridge. Okay? Your fridge starts to run. Because what's happening in your fridge is you've got coolant. I have a picture of it somewhere else here. Right here. Okay, so in your fridge, you've got little pipes that run all throughout the fridge. Okay, the top of the fridge, the back of the fridge, bottom of the fridge. Okay, and if you've got a fridge freezer, okay, it's still just one compressor. Right, unless it's two separate units. But if it's one unit, okay, you've got one compressor, okay, and you've got these coolant lines. So as the heat comes off of your food, it's absorbed by the coolant. Okay? And what the coolant does when it absorbs energy is it changes state from liquid to gas. Okay? And that takes a lot of energy. Okay? So it changes state from liquid to gas, and now the food inside has lost energy, and it's as a result cooler and staying cold. Okay? Now the compressor, okay, is what takes that now gaseous coolant and forces it back into a liquid. When you force something back into its liquid state, all the energy it absorbed to change into a gas has to be released. Okay? So the compressor is the part of your fridge that gets hot. Okay? It's turning that coolant back into a liquid, and then there's a fan underneath that blows the heat that comes from that out into the environment, okay, into your house, essentially. Okay? That's why there's always warm air coming out from under your fridge when it's running. Okay? It's keeping things cold by pumping the heat from inside, where it's supposed to be cold, outside where it's warmer, which goes against the second law of thermodynamics. Energy is supposed to go the other way. Okay? So if you're going to make energy go backwards, okay, then you have to use energy to do that. Just like active transport has to use energy to pump stuff up the concentration gradient, okay, a heat pump has to use energy to make energy go the other way as well. Okay? Your air conditioner does the same thing in the summertime if you have air conditioning. It takes the warm air in your house, okay, cools it off, and then pumps that heat outside where it's hotter. Okay? Because you want it around 22 degrees in your house, but it's 30 degrees outside. Okay? Well, it's got to take the heat it absorbs from the air in your house and pump it out to where it's 30 degrees already. Okay? That sort of makes sense to everybody.
So technically every single time you turn on your air conditioner inside your house, it gets warmer outside the house?
Yep. That's exactly what I'm saying. Next time your air conditioner is running, just go stand over. You can feel the heat coming off of it. Okay? It works. It's exactly the same as a fridge. It's just a really big fridge. Okay? Your air conditioner has exactly the same setup. It has a compressor. It's just much bigger. Okay? And it's pulling air from inside the house over that compressor, over the coolant line, okay? And then the compressor is pumping out the heat. Okay? Everybody all right with that idea? Okay? So a heat engine uses the second law of thermodynamics to do useful work, and a heat pump tries to circumvent the second law of thermodynamics by making heat go the wrong way. Okay? All right. So this stuff here that I've underlined, okay, is important. So the process is not natural. So work must be done by the refrigerator. Energy has to be pumped, okay, to a refrigerant, okay, that can then take it out. Okay, so that thermal energy is transferred into the air surrounding the refrigerator. Okay, the refrigerant is pumped into a condenser or compressor. Okay, it's cooled and liquefied, and the cycle repeats. Okay, so could you pull a Homer Simpson and try to cool your house with your refrigerator? Like if you just leave the fridge open, will it cool the house? Remember, Homer built this tent. I don't know if you guys saw this episode. It's really old because since it's been running like longer than you've been alive. Okay, his explanation was it was really hot, and I opened the fridge probably to get a beer because he's Homer. Okay, and I noticed that it was cold in the refrigerator. And so what he did is he just built, like he took a bed sheet or something and he built a tent over the refrigerator. He just hung out there because, I mean, why not? It's cold and there's beer. And then so it was great for him because that's, you know, the things that Homer wants. So if I just left the fridge open, could it cool the house with my fridge? No. Where's the fridge trying to pump the heat? Into your house. So if you leave the fridge open, the fridge is pumping the heat and then sucking it back in. Okay? All you're going to do is exactly what happened to Homer. He destroyed the compressor on his refrigerator because it's just going to run continuously because it can never catch up. Okay? It's trying to cool the area it's pumping the heat into. Okay? That would be like taking a big pipe on your air conditioner and running it back into the house. Okay? It'll just run continuously then because it'll pump all the heat it absorbed back into the place it absorbed it from, and it'll never quit. Okay? So no, you're not going to be able to do that. Okay? And it didn't work for him either. All right. I want you guys to answer the circled questions there. Okay? Put them in your own words. First law of thermodynamics. Okay? Distinction between work and heat. Okay? Identify whether the following is best explained by the first or second law of thermodynamics. You don't need much explanation there. Okay, state the second law, right? And then 9 and 10 are kind of explanation questions. So give you a few minutes on those and then we'll go through them together.